outside, and this term we will have here. Okay.
You want to continue, sir?
Let's finish this question. Okay.
Sir, because the tea will
Okay.
become cold.
Okay. Let's take break.
Sorry.
Yeah. Let's take break. Let's take one by one. So this code is about BPSK simulation for the relic feeding channel. Okay. So this is the debug mode. So I am running each line one by one. CLC clear, you already know. CLC clear the command window and clear the workspace, delete all the variables. Okay. And RNG1 is to initialize the random number. Okay. Now I go to another step. Since I am doing BPSK, so I have chosen S is equals to plus minus 1. Okay. NS represent number of symbols for the simulation. I have chosen 1E4. It means 10 to the power 4. IRND, it means I am generating.
He's writing comments, sir, so that they will understand.
Okay. I will write comment here. So this is BPSK. BPSK constellation. These are the number of symbols, and these are the number of, I want to generate a data stream. Okay. So I will not transmit only like 1 bit or 2 bit. I will transmit a stream of numbers, right? Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. For that, I need to generate a random stream. Okay. So this command generates random number. Random stream generate. So
Integer or something like that.
yes. So this rand_i command generates. So if I write 2 here, so I can press F1. So it will give me the information. So rand_i2 means it will give me the random number up to 2. So 1, 2. If I write rand_in, so it will give me random number between 1 to n. Okay. And how many random numbers I want to generate? I want to generate 1, ns, the size of the random numbers. So this second argument represents the size. So ns is equal to 10 to the power 4. So this will generate 10 to the power 4 random numbers 1, 2, 1, 2. Okay. Let's check it whether it's generate or not. Okay. Let's go to the next step. So here you see this is showing a preview of some of the values of IRND variable. So this is 1, 2, 1, 1, 1. Okay. So this is generating random values between 1 and 2. Okay. Why we are generating 1 to 2? Because our BPSK has constellation has only 2. So if I write here in the next line x equals to SIRND, so it will generate plus 1, minus 1 for all of the stream. Okay. Let's go to this step. So this x will be minus 1 plus 1. So this will generate the whole stream for 10 to the power 4 numbers. Okay. This part is clear up to? So this is what? This is BPSK stream. Now what I am doing here, I am generating here noise. Okay. So when I transmit 1 bit plus 1 or minus 1, I will get that much noise. So I am generating 10 to the power 4 values for noise. So noise is complex Gaussian distributed. Okay. And each part has half the variance. Okay. So this is the rand_n generate what? Gaussian distributed random variable with 0 mean and unit variance, but each has half. So I will divide by square root of 2. So its variance become half. So half and half becomes 1. So this is the imaginary part, this is the real part. Total, the variance is 1 and mean is 0. Okay. So this is the way we generate what? Complex Gaussian random variable for noise. Okay. So let's move to the next line. So this is the dimension of it is 1 cross 10 to the power 4, and this is a complex variable. Okay, so these are complex values. So this nh, I have taken another variable because we have another random variable that is called the channel. So channel, we will also generate some values because we have to take the average. So first we will check the probability of error for fixed channel, then we take the average. The thing we have done in the when deriving the derivation, doing the derivation. First we choose the fixed h, then derive the probability of error, then we take the expectation over h, right? So we, for that, we take an nh equals to 100, we will average over 100 channel realization. Okay? So this represent number of channel realizations. Okay? This one is noise, circularly symmetric Gaussian noise. Okay. So next I generate the channel. Channel I generate with cn01 variable, that is 0 mean, unit variance, or the size of it is 100. Okay. So this is the real part and this is the imaginary part. I have to write 1i here for the imaginary part, and then square root divided by 2, because each will have, real part and imaginary part have half the variance. Okay. So this is the way which I will generate the channel. Okay. And how many channels I will generate? I have chosen number of realization to be 100. So I will generate 100 cross 1 vector for that. So this h will be, since I have made some change here, I have to save it and rerun it again. So this h is 100 cross 1 vector. Okay. Now I want to plot my bit error rate versus the SNR. Okay. So the SNR, I will change the transmit power. So transmit power I have chosen between 0 to 40 dB. Okay. So this linspace command generates values, it will generate 15 values between 0 to 40 equally spaced. Okay. So it will generate 15 values. So this PDV has 15 values and minimum value is 0 and maximum value is 40, and these are equally spaced. Okay. So NDV, I have chosen the length of PDV, that is 15. Okay. Next, I chosen the variable PE for probability of error that I going to assign. So I have just initialized that variable. So I have two indices here, one for NH for each channel realization and each transmit power, that is NDV. Okay. So for each transmit power IDV equals to 1 to NDV, I am running the loop, and for each transmit power I am assigning P2. So this above 0 to 40 was in dB. So I am converting it dB into normal power by using this function dB to pow, and PDB is my this variable, and I am choosing particular index IDB which is ranging from 1 to NDB. So in each iteration it will give me one of the values from the array, that is PDB, and it will convert it to power. Okay, from dB. Okay. So let's go to next line. So this P is equals to 1 here. Why 1? Because the IDB is 1 and PDB is initially 0. So 0 dB is 1. Okay. So now I am doing for each channel realization. Each channel realization I am running the loop IH equals to 1 to NH. So this is my loop index IH. Okay. So I have taken channel H equals to IH. I took the channel one by one, and I have written the equation here, y equals to H into X into square root of P, that is the transmit power, plus noise. Okay, H is my channel, H is my channel, and H is my transmitted vector, plus 1 or minus 1, and square root of P is my power, and W is my noise. So this is what I will receive. Okay. So what is the size of it? Y equals to 1 cross 10 to the power 4. Okay. So what is the size of H? H is 1 scalar value. What is the size of X? X is 1 cross 10 to the power 4. And this is also scalar, and W is 1 into 10 to the power 4. So this, the first thing in this sum, this is a vector and this is a vector. So the output is a vector, 1 cross 10 to the power 4. Next, what I have to do? I have to detect it from Y. So the decision rule I explained earlier yesterday. What was I doing? Real of Y divided by H greater than 0. If I have greater than 0, I will choose plus 1. If I have less than 0, I will choose minus 1. Okay. So in MATLAB, so this is like a hard decision. So in MATLAB, if I write this, it will give me either 0 or 1. So this is like a Boolean expression. Okay. So this is either true or false. So if I write this, the output of this will be either 0 or 1. So I have to compare 0 and 1 with minus 1 and plus 1. So what I have to do here? I have to convert 0 and 1 to minus 1 and plus 1. So that's why I have written 2 into minus 1. So it will convert my 0 and 1 to plus 1 and minus 1. Okay. So that way I will get the estimate of my transmitted value. Okay. That is x1. Next, what I have done here? I have written here x1 not equal to x. Whenever x1 not equals to x, those will be true and false. It will come, and mean means it will count those true or false, and it will take the mean value of it. So this will give me the probability of error. This part is okay. So it's just an expression. This will give me the Boolean expression. Okay. So x1 is what? 1 cross 10 to the power 4, and x is also 1 cross 10 to the power 4. So we can compare both of the vector because both of the length are same, and we will get plus 1 or minus 1 accordingly, 0 and 1 accordingly. Okay. So mean means it will take the mean of ones. It will take the sum. So 1 will come when values are not equal, when this condition is true. The condition is what? x1 not equal to x. Okay. Clear? So this will give me probability of error for a particular channel realization, and this loop will run for each channel realization. Okay. So I am collecting all the probability of error for different channel realization in the variable PE for all channel realization, and also as well as for all different transmit powers. Okay. Which I have already initialized this variable, and I am taking each value here one by one. Okay. So for example here, let's check this value, what this will be. Evaluate. Let's see the command window. So it is showing me 0.0436. This is the probability of error for this particular realization at 0 dB. Okay. If channel realization will change, this value will also change. If noise will change, this value will also change. Power will change, then this value will also change. Okay. So after I have run both of the loops, I will get up to here. So let's stop it and run the whole program and reach up to here. So if I run it, I will get up to here. So I will get this probability of error, which is of 100 cross 15. 100 for what? Number of channel realization, and 15 is for what? Number of transmit power values I have chosen. Okay. Now for each channel realization, I will take the average. So I have written here mean PE comma 1. Comma 1 means the first dimension. So in a matrix, the first dimension is row wise, second dimension is column wise, and the third dimension is, and so on. Okay. So here I have to take the mean with respect to the channel. Channel is the first dimension. You see 100 here. It is the first dimension. Okay. So after that, I will get how many values? 15 values corresponding to each transmit power. Okay. So each transmit power. Now I can plot this. I have written here figure 1 comma CLF. CLF means clear figure. Figure 1 will generate the empty figure. Now I write here plot PDV, PE comma 1, hold on. And then I am in the second thing, what I am doing, I am plotting for any realization, let's say PE second channel realization, I am also trying to see what happens for a particular channel realization. So I am just plotting here, okay. And set GCA Y scale log. So what does it do? It converts the Y scale into the log scale. Okay, so it will be a semi-log plot. Okay, GCA means get current access. GCA. And then I have chosen to on the grid. So it will turn on the grid. Okay. So I will get this kind of curve. So the blue curve represent my BPSK simulation with Rayleigh fading, and this red curve for a particular realization, channel realization. Okay. Any question up to this point? Huh? Flat fading channel. Frequency selective channel, either we have to use the CDMA or we will use the OFDM normally. Okay. So that thing is different. I mean, that is like a very big simulation. Okay. If we are teaching it, we will cover it. OFDM I can easily OFDM also convert the frequency selective channel into frequency flat channel also. So OFDM is mostly used if we have wideband.
Can I answer that?
Yeah.
Madam, frequency selective, yeah, ma'am. Why we use flat fading means basically flat fading means we have over the bandwidth of the channel we use flat response. It is constant value, na? Constant value means the constant value we can use it for simulation. Yeah, if it is a frequency selective means if it changes like this randomly, zigzagly, what we have to do, yeah, up to how much our constantness is there, will, yeah, like non-linear things we can't use, right? How do we use non-linear things? We split the non-linear things into linear things, small parts, and in that small part it becomes linear. Similarly here also frequency selective means, yeah, up to a little part, a little bit of bandwidth only it is constant. Over that little part only we can use. So frequency selective channel means we can use over that flat fading. We have to divide the frequency selective channel into flat fading channels. You understand? You are understanding what I am telling now? H is constant. Yeah, that again depends on the channel you are using. It depends on the channel you are we are able to use even frequency selected chart also. Yeah. Yeah, piecewise changes. Yeah. You understood now? Okay, sir.
Okay. Any question here in this BPSK simulation? This is easy, right? Okay. So I have another simulation that is for QPSK. Okay. This is slightly different. Most of the part is similar. Yes. Yes, more symbols will be there. So this is just for a point-to-point system. One transmitter, one receiver, single antenna. Okay. So, okay, let's continue. So first is CLC clear. Then we define the QPSK constellation. So QPSK constellation has 4 points. Okay. So these 4 points are -1 minus I, -1 plus I, minus +1 minus I, +1 plus I. Square root of 2 for the normalization. Okay. So 10 to the power 4 number of symbols, and these are the to generate the random stream. So here I have written here length of S. So length of S is 4. So it will generate the random number from 1 to 4. And how many random number it will generate? 1 cross 10 to the power 4. NS is 10 to the power 4. So this X will be 1 cross 10 to the power 4. So let's run this and see. So this IRND, it is showing some preview. 2, 3, 1, 2. Okay. So it will generate between 1 to 4. And the value of X is accordingly. Okay. So next is W. So this is the noise, the same way. Then I choose a 100 channel realization. Then I generate the channel in the same way. Number of transmit power values I have chosen to be 15 between 0 to 40 dB. NdB is the length of this, that is 15. And P is the probability of error. In that variable I will assign all the values. So I just indented the code so that it can be easily understandable. So let's run up to here. Okay. So we are now here. So let's run it. So for each transmit power, I choose the index IDB equals to 1. It will convert to the from dB to power. And for each channel realization, I will write the same equation, y equals to hx into transmit power plus noise. And here what I am doing here, I am doing here ML decoding. Okay. In ML decoding, what we have, y minus hx, we have to find out the x over all possible values. Okay. So here y is my 1 cross 10 to the power 4. Okay. And h is a scalar. H should be complex. Okay, one I is remaining here. So H is complex, and then S is what? S is our vector 4 cross 1. For each y, I will check whether this difference is minimum for which of the values. Okay, whichever value of S gives me the minimum, I will choose that value. Okay. So if I select this and run this, evaluate, I will get some values like this. So the size of it, how many it will be? 4 cross 10 to the power 4. For each value, I am comparing with 4. Now, for